Greetings! Today we are starting gravity. Going to be specifically talking about the force and acceleration due to gravity in places other than near the surface of the Earth. That's what we've always been doing with gravity, just what is it up to near the surface of the Earth? We're going to expand beyond that today. We're going to use what we learned today to find a bunch of interesting things. We're going to find the force of gravity on astronauts on the space station. We're going to use this to find the radius of geosynchronous orbit. We're going to use this to find the mass of the Earth only knowing the orbit of the Moon. And then we will use this to find the force of gravity on objects that are actually inside the Earth, at different radii inside the Earth. So it's going to be fun. So what are the new equations that we're going to be using for gravity, force of gravity, and acceleration due to gravity? Reminder, the old equations were that the force of gravity is equal to mg. I remember being very annoying, trying to always remind you of that. And the old acceleration due to gravity was just g, 9.8 meters per second squared. The new equations that we're going to be using are that the force of gravity is equal to big G times m1 times m2 over r squared, and the acceleration due to gravity is big G times m over r squared. Now, you can see these equations, but if you don't know what anything means, then it's kind of useless for you. Big G, Newton's gravitational constant. It is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. No one is going to make you memorize that. That's way too much to actually have to memorize. You will probably end up memorizing 6.67 times 10 to the negative 11 just because you'll use it so many times. But it's useless to memorize because you can always just go online and figure it out. The m1 and m2 here are the masses of each body. You cannot have the force of gravity on an object without two objects. You need one object to have the gravity and one object to be affected by the gravity. So you need the mass of each object. You see pretty quickly that it doesn't matter which one is which. Either one can be put in either place. So that means that the gravity, the force of gravity of the Earth on the Moon versus the force of gravity of the Moon on the Earth, think about that. Which one is going to be greater? The force of gravity of the Moon on the Earth or the Earth on the Moon? Well, according to this, it should be the same thing. The Earth is a lot larger, and so it has more possible gravity to be pulling down on things, but the Moon is very small, so it doesn't represent a very big target for the gravity to interact with. Whereas the Moon is much smaller, but the target of the Earth is much larger, and so there's more there to pull down on. Therefore, the force of gravity, the difference in masses cancel out, and the force of gravity of the Earth on the Moon is the same as the force of gravity of the Moon on the Earth. R is the distance between the centers of the objects, not the surfaces, the distance between the centers of the objects. That's going to be very important very shortly. You will always be given these kinds of equations because, again, you can just find them online, so why bother making you memorize anything? Here is the first kind of question that I can give you. It's plug and chug though, so there's not much to it. What is the force and acceleration due to gravity on you on the surface of the Earth versus you on the International Space Station? So what is the force of gravity on you when you're on the surface of the Earth versus what is the force of gravity on you when you're on the ISS, International Space Station, and again with acceleration due to gravity instead of force. I give you some constants. The radius of the Earth is 6,371 kilometers. The distance of the ISS's orbit is 405 kilometers. Here's the equations. Let's just estimate your mass to be 75 kilograms. And let's calculate it out. Well, you don't want to watch me just calculate these things. So I already did it. The force of gravity on you when you're on the surface of the Earth is 735.8 newtons. The acceleration due to gravity when you're on the surface of the Earth, according to this equation, plugging in the mass of the Earth there, and the distance to the center of the Earth there, and big G there, that gets you 9.81 meters per second squared. I did make this list of important constants. The mass of the Earth is 5.97 times 10 to the 24 kilograms. We've got the radius of the Earth. We've got gravity. Now, what are two different common mistakes that you think people will make when trying to solve this? They both involve something here. Well, in my time as teaching, one of the most common mistakes is to leave this as kilometers. And when you just plug it in as kilometers, well, the equation doesn't know what you're doing, and so it interprets it as meters, and you get off by a factor of 1,000,000, actually, because the wrongness here is a factor of 1,000. If you just plug in 6,371 instead of 6,371,000 meters, you plug that in wrong there, you end up being off by a factor of 1,000,000, which you probably don't want to be doing. The other thing that a lot of people will get wrong is they'll say, well, I'm on the surface of the Earth. That means my height is 0. Okay, well, I'd better plug in 0 right there. What's going to go wrong there? Yeah, you don't want to divide by 0. That creates other problems. If you plug it in right, and you should try this at home with your calculator, you should find that the force of gravity on you is 735.8 newtons, acceleration 9.81 meters per second squared. That compares to the old equations. This is just mg, 735 newtons. Well, it's close enough. And then just assuming 9.8 meters per second squared for g, it's close enough to 9.81. The reason that we don't go to 3 significant figures in this class is because the acceleration due to gravity actually changes a little bit as you change position on the surface of the Earth. Different parts of the Earth will have different accelerations due to gravity. And it's a small difference. It's from 9.79 to 9.83 meters per second squared. So not a big deal, but it's because here in Florida we're near so much water, which has low density, that I think that we have very slightly lower gravity here, I believe. Whereas if you live near a big mountain, like in a valley between two mountains, you might be experiencing more gravity. But if you're at the very top of a very tall mountain, then you might be having less gravity because you've got a larger value for r, the distance that you are from the center of the Earth. There's a lot of different things that go into it. And actually, scientists are using differences in the acceleration due to gravity to find mineral deposits and oil deposits underground. It's actually really neat. Using greater and lower gravities as you go around the surface of the Earth to find out what is under the Earth, because different masses underneath your feet will actually change how much gravity you have at your exact location on the surface of the Earth. Anyway, the number can vary, and so we just round to a value that's close for everyone instead of going crazy trying to figure it out exactly where we are right now on the surface of the Earth. If you do all this again for the International Space Station, you'll get these numbers. What is something that I bet a lot of people are going to mess up on when doing this, finding this for the International Space Station? Do you think that the space station orbits the Earth 405 kilometers from the center of the Earth? I'm going to guess no, because that would put it extremely deep underground. If that's the radius of the surface of the Earth, we do not expect the space station to be orbiting around inside the Earth. However, the height of the orbit of the International Space Station is always quoted as this, 405 kilometers, give or take, because that's how high up it is. A lot of people will plug that directly into r squared. Even if they convert it to 405,000 meters, that's still going to get you a very, very wrong answer plugging it in for r. You have to, what do you think you have to do? You have to add 405 kilometers to 6371 kilometers and convert that to meters. Either convert it before or convert it after you add them. If you actually do that, you get the force of gravity is 605.4 newtons instead of 735.8, and the acceleration due to gravity is 8.67 meters per second squared. You are not weightless in space. You do not experience no gravity in space. You do experience gravity in space. You are just orbiting the Earth. And when you are orbiting the Earth, you're in free fall. And so all of your surroundings, the space station that you're in or whatever, it's all falling with you. And if it's all falling with you, then you can't tell that gravity is acting on it. If you are in a very, very tall building in an elevator and the elevator cable snaps and you start falling down, you're going to be falling at the same rate as the elevator, accelerating at the same rate as the elevator, and so you will just tend to float in the middle of the elevator as it falls. That's why it would appear that you would not be experiencing gravity in that falling elevator until, the end of the ride. Same thing for the ISS. It's just that we put the ISS in an orbit so that it never falls down to Earth. It continuously circles the Earth. You still experience quite a bit of gravity on the space station, so you are not weightless, even though a lot of people call it that. That's imprecise. The space station takes about 100 minutes to orbit the Earth once. So a lot less than one day. The moon takes about 29 days to orbit the Earth once. A lot more than one day. That implies that something between the space station and the moon could take possibly one day to orbit the Earth once, if you just put it in the exact right place. This is called a geosynchronous orbit. It's used very commonly with communication satellites. Put a communication satellite in an orbit that takes exactly one day to go around once, and when the Earth turns around once in 24 hours, the satellite will go around once in the same 24 hours. That means that you can just point a satellite dish at a particular patch of sky, and the satellite should stay in that same apparent part of the sky at all times, because it's just hovering over the same point on Earth all the time, or it's really more accurately continuously falling over the same point on Earth all the time, because it's in orbit. But we want to find out how far up we should send that satellite to get it into a geosynchronous orbit. Well, how are we going to do that? We're probably going to end up using that g, the acceleration due to gravity, is equal to big G m over r squared. That's how we can get an r into all of this. But g, that's the acceleration due to gravity. Ask yourself, what direction is that pointed? If I have Earth here, and I have my satellite orbiting the Earth, here's the satellite, what is the direction of gravity? Well, it's always inward. That is the direction of the force of gravity, and the acceleration due to gravity, because acceleration always lines up with force. If it's always pointing inward, then what clue does that give us? Yeah, we should probably be using that the centripetal acceleration is equal to v squared over r, which is also equal to r omega squared. I'll tell you that using omega is probably going to be our best bet for finding out what to do with this. The centripetal acceleration is equal to the acceleration due to gravity. AC centripetal acceleration is equal to the acceleration due to gravity because the centripetal net acceleration, or force, is equal to the mass times the centripetal acceleration. The net centripetal force is equal to the mass of the object, the mass of the satellite, times the centripetal acceleration. The only force acting on the satellite is the force of gravity. So if we replace the force of gravity there, then this would be the mass of the object times the acceleration due to gravity. And the only difference between the force of gravity and the acceleration due to gravity is we dropped an m, which you can see if I plugged in this in there, this equation right there, in for that, then you'd be able to cancel out one of the masses in there, and you'd be left with just this, that the centripetal acceleration is the acceleration due to gravity, and it's gm over r squared. Let's use this. We need to find omega. Well, omega is just how much angle you go through in how much time. Okay? In one day, how much angle are you wanting the satellite to go through? We want it to orbit once every 24 hours, so we want it to go in one full circle in one day. Well, that's 2 pi radians in one day. But I can't put one day down here. What should I put? Yeah, I need 86,400 seconds. 86,400 seconds. When I calculate this out, I'm going to get radians per second. So 2 times pi divided by 86,400 seconds gets us a tiny number. What is that tiny number? It is 7.269 times 10 to the negative 5 radians per second. That is our omega. We can plug that in up there for omega. Well, I need to combine these equations. If the centripetal acceleration is equal to the acceleration due to gravity, I can combine these. Therefore, these are equal to each other by the transitive property. G m over r squared is equal to r omega squared. I can multiply both sides by r squared and divide both sides by omega squared. G m over omega squared is equal to r cubed. Therefore, r is equal to the cube root of g m over omega squared. If we get our important constants back out, we can solve this. We've got the g 6.67 times 10 to the negative 11 times the mass 5.97 times 10 to the 24th kilograms. Earth is quite large. Divided by omega, which we had here. Let's square that. And we need to take the cube root of that. And we get that the radius of the orbit is 42,167 kilometers. A 1,000 kilometers is 10 to the 6 meters, and so 42,000 kilometers. Is that right? Is that what you hear when you talk about geosynchronous orbit? No, whenever anyone quotes geosynchronous orbit, it's something like 35 to 36,000 kilometers. Why is that? Well, if we take this, I'm going to divide it by 1,000 to get it into kilometers, and I subtract 6371 from it, suddenly I get 35,796 kilometers, which is extraordinarily close to the accepted value. This number that we have here includes the radius of the Earth. In effect, you have the Earth, you have the satellite orbit overhead. This number is from the very center of the Earth out to where the satellite is, whereas the number that you always hear is from the surface of the Earth out to wherever the satellite is. That's the reason for the discrepancy right there. Be very careful to always include that when you're thinking about these kinds of numbers. People will sometimes ask me, how on earth do we find the mass of the Earth? How did people 100 years ago or 200 years ago figure out the mass of the Earth? Well, the answer is they used the moon and the orbit of the moon to do this. We've known for a long time how long it takes the moon to go around the Earth. And with some pretty easy math, we can say, okay, if it goes around the Earth in 27.32 days, and once around the Earth is 6.28 radians, we can take 6.28 radians divided by 27.32 days, convert that into seconds, actually, and we can find the angular velocity of the moon around the Earth. 2.66 times 10 to the negative 6 radians per second. Be sure that you can figure that out. We also can find the distance to the moon. How do we do that? Well, one way that people can do that is they can say, well, here's the Earth, and the moon is out there somewhere, and you can have one telescope on this side of the Earth and another telescope on this side of the Earth, greatly exaggerated. They each look at the moon, and they would see it in slightly different positions. Just like our eyes give us parallax, give us depth perception through parallax, looking at the moon from two different positions, it would seem to be in front of different background stars. In one perspective, it would be around those background stars, and another perspective would put it around a different set of background stars. You can measure that angle, and with that angle, this angle in here, with that angle and the distance between this telescope and this telescope, which is just the diameter of the Earth in this case, you can find the distance to the moon. That has been known for hundreds of years, actually. So, the distance to the moon is well known, and the period of the moon's orbit is well known, therefore the angular velocity of the moon's orbit is well known. We can use that and a bunch of equations. We've already discussed how the acceleration due to gravity is gm over r squared, and we've discussed the centripetal acceleration is r omega squared, and we've discussed that the centripetal acceleration is equal to the acceleration due to gravity because that's the only force available to it. Therefore, we can take out the middleman and say that gm over r squared is equal to r omega squared, just like we did in the last problem. You do the algebra, and you find that the mass of the Earth, which is going to be that m right there, the gravitating mass, is equal to r cubed omega squared over g. We know r, we know omega, we know g. And we get a mass of the Earth 6.056 times 10 to the 24 kilograms. That's actually off from the accepted value of 5.97 times 10 to the 24 kilograms. Not by very much. We're off by about 1% between these two. The reason that we're off by 1% is just a bunch of rounding. Once around the circle is a little bit more than 6.28 radians because pi is a little bit more than 3.14, and so 2 pi is going to be more than 6.28, and the distance to the moon and all these things are off by just a little bit, and altogether they end up making us off by about 1%. So for a normal person, you probably don't need to be any more accurate than 1%. If you are working for NASA or SpaceX or Blue Origin or someone, then yeah, you probably want to be off by less than 1%. But we don't have to worry about that. 3 significant figures, whatever, it's fine. And I'll take it. 1% off is good enough for me. But that is how people could find the mass of the Earth even hundreds of years ago. Here's something that I think is actually pretty fun that you can do with all this gravity stuff. A lot of people have wondered what the gravity is deep inside the Earth. If anyone has seen that old and very terrible movie called The Core, you might know what I'm talking about. What is the gravity deep inside the Earth? If you go thousands of miles into the Earth, what kind of gravity would you experience? I want you to think about this. Ask yourself, if I dug halfway to the center of the Earth, would I experience a lot more, a lot less, a little more, a little less, the same gravity that I experience on the surface? Think about that. Another question, what if you went to the exact center of the Earth? Would you experience a lot of gravity? A little gravity? No gravity? Infinite gravity? All good questions. It turns out that when you take, approximately 4,000 level physics, maybe 3,000 level physics, you'll be able to show mathematically that you should only count the mass of the Earth that's below you when you are calculating the gravitational pull of the Earth on you. Let's say that you drilled a gigantic hole all the way through the Earth, from this side of the Earth to the other side of the Earth, and you had a ball that you dropped into this hole right there. It turns out, doing all the math, that the mass here would cancel out the mass here. Now, what does that mean? Okay, we need to draw some imaginary lines. First imaginary line, the ball is dropped down into the Earth somewhere. Well, you draw an imaginary line just straight across the Earth that is perpendicular to the tunnel that you've drilled. So you drill a tunnel, you draw a line perpendicular to that going right through where the ball is at that moment that you want to find out the gravity at that location. Draw that line. Then you draw another imaginary, I guess it's a plane that you've drawn there. Now you draw an imaginary sphere whose radius is the same as the distance from the center of the Earth to where that ball is. So center of the Earth is there. The radius of this sphere is the same as the radius of the distance that that ball is from the center of the Earth. That is now 2 imaginary surfaces that you have drawn. If you take the mass that is in this region here, above the imaginary plane that you've drawn through where the ball is, that mass, compare the gravity from that mass to the gravity from the mass that is on the other side of that imaginary plane, and also outside of this imaginary sphere. So we've got our mass up here, and we've got our mass around here. If you calculate the gravity from this chunk of the Earth and the gravity from this chunk of the Earth, excluding this part, you'd find that the gravity of this part above is exactly equal to the gravity of this part on the other side when viewed from that point. That's a weird and interesting result, but it is incredibly convenient because now all of the mass that is farther away from the center of the Earth than you are doesn't count. You are 1,000 miles down or something, I don't know. Any part of the Earth that is less than 1,000 miles down is not going to count when calculating gravity at your point. Only the matter that is closer to the center of the Earth than you are actually counts when doing any of these kinds of equations, when trying to find the acceleration due to gravity inside the Earth. Only count the mass that's below you. What I want to do is I want to make a graph of the acceleration due to gravity at any particular radius, any particular distance from the center of the Earth, which includes, on this graph, points that are below the surface of the Earth and points that are above the surface of the Earth. Let's try that. Well, I actually got all the math here. The gravity inside the Earth. We start with the standard equation. Acceleration due to gravity is gm over r squared. The m is the enclosed mass, the mass that is closer to the center of the Earth than you are. And r is the distance that you are from the center of the Earth. What is the mass of the stuff that is closer to the center of the Earth than you are? Well, the mass of the stuff that's enclosed, closer to the center than you are, is the density of that material times the volume that is beneath you. Well, that volume is just the volume of a sphere, 4/3 pi r cubed, but that r is the distance between you and the center of the Earth, or the center of the Earth and you, because that is the stuff that is below you. The acceleration due to gravity at any particular radius, any particular distance from the center of the Earth, is going to be equal to this, because we can just take this volume right there, plug it in for that, and then we'd have rho times 4/3 pi r cubed. We can plug that in up there, and then we'd have g is equal to g rho 4/3 pi r cubed divided by r squared. Well, you get rid of the r squared and two of the r's and the r cubed, so you just have an r remaining, and you get that the acceleration due to gravity at some random radius inside the Earth is equal to g times rho times 4/3 times pi times the distance that you are to the center of the Earth. Okay, there's a whole lot of stuff there. How can we simplify this? I actually went through some iterations on how to simplify it best, so I've got little post-it notes covering up old versions of this. But the mass of the Earth should be, well, the density of Earth times the volume of Earth. So the mass of the Earth is going to be rho times 4/3 times pi times the radius of the Earth cubed. I just have r naught there, r sub 0, but that, just pretend that that means the radius of the Earth there. I can divide both sides by r naught cubed and get the mass of the Earth divided by r naught cubed is equal to rho times 4/3 pi. But I've got a rho times 4/3 pi right there in the previous equation. I can replace this rho 4/3 pi with the mass of the Earth divided by the radius of the Earth cubed. That gets me that the gravity on at some random point, random radius inside the Earth should be g times rho 4/3 pi, or yeah, rho 4/3 pi, but that's equal to the mass of the Earth divided by the radius of the Earth cubed times r. Right there, the radius that we are at, the radius that we are testing at. I can then say that the acceleration due to gravity at some radius, I can take that, take one of those r naught, the radius of the Earth, take one of those out, so it'd be radius of the Earth squared times radius of the Earth in the denominator, and move that over like that. So I've got radius of Earth squared times radius of Earth there, move some parentheses around, and then I get g times the mass of the Earth divided by the radius of the Earth squared times the radius that you are at inside Earth divided by the radius of the Earth. Well, remember, the gravity at the surface of the Earth, that says surface, gravity at the surface of the Earth, the acceleration due to gravity, is g times the mass of Earth divided by the radius of the Earth squared, which is right there. So I can then replace that and say that the gravity at some random point within the Earth is going to be equal to the gravity on the surface of the Earth times the radius that you are at divided by the radius of the Earth. So, when you're at a radius of 0, where would you be at a radius of 0? Yeah, you'd be at the core of the Earth. If you're at the core of the Earth, then, well, 0 divided by whatever, I don't care. You have 0 gravity at the center of the Earth. If you are at 1/2 the radius of the Earth, then you'd have 1/2 the radius of the Earth divided by the radius of the Earth, and you just have 1/2. And so the gravity at that point, halfway between the center of the Earth and the surface of the Earth, would be half of the gravity at the surface of the Earth. We can graph this. Here, we said that at the center of the Earth, this is the center, this is the radius that we are at, this axis, and this axis is the gravity at that point. Well, when we are all the way at a radius of 0 at the exact center of the Earth, we have 0 gravity, 0 acceleration due to gravity. At the surface of the Earth, we have 9.8 meters per second squared of acceleration due to gravity. And according to this, it is a linear relationship within Earth, inside Earth. Therefore, the function of gravity should look about like this. It should be a linear graph inside the Earth. So if you are halfway between the surface of the Earth and the center of the Earth, then you should have half the normal gravity of the surface of the Earth. Above the surface of the Earth, it behaves just as we have said before. The acceleration due to gravity is equal to g mass of the enclosed mass, which is just the whole mass of the Earth, divided by r squared. So a 1/r squared kind of graph looks about like this. This is the function of gravity beneath the surface of the Earth and above the surface of the Earth. Here, it's linear and increasing with radius because you have more and more mass underneath you as you go out. Then you have more and more mass underneath you, which can give you more gravity. And then away from the surface of the Earth, outside of the Earth, then the higher up you go, the greater you're increasing r, but you're not adding mass. When you move from there to there to there, you're not actually adding any mass getting farther away from the Earth anymore. And so the 1/r squared term becomes important, and you just get less and less gravity as you get farther from the Earth once you're outside of the Earth. I think that's pretty cool. You can have a lot less gravity if you are inside the Earth, but it still wouldn't exactly be a comfortable place to go.